So the question we should ask ourselves, if there's a matching of the relative order with the millions of years ages, which are highly inflated, of course, compared to the biblical timescale, we have to ask ourselves, why should radioactive decay rates have always been constant at today's measured rates? Why should that be an assumed constant? What if radioactive decay had changed in the past? If it had, and the clocks tick faster, then we couldn't use them to measure the ages of rocks. Well, I was involved in an 8-year project initiated by creationists called the Radioisotopes and Age of the Earth Project, the RATE project. And that project concluded that assumption number 3, that is, the constant decay rate assumption, is absolutely false. And I want to demonstrate that to you tonight. In this project, we discovered 5 independent lines of evidence that demonstrate that radioactive decays must have been grossly accelerated during one or more recent catastrophic geological events, especially during Noah's flood. Now, that makes sense. If we had catastrophic rock formation and other geological processes during the flood, why not catastrophic rates of radioactive decay? So if that's the case, and the clocks tick faster in the past, radioactive dating cannot be used to accurately give us the absolute millions of years ages that are claimed for the rocks. Well, let's look at these evidences. Number 1, helium in zircons. Zirconium silicate is a little mineral called zircon, and in zircon, these zircon grains, they contain uranium. They're highly radioactive, and as a result of having the uranium. And as the uranium decays, a byproduct of that decay is helium. So every uranium atom that decays actually produces 8 helium atoms as a byproduct. Now, some years ago, there were investigations into potential geothermal energy in the Los Alamos area of New Mexico. And in this drill hole, they intersected a granite. And in the granite, we find these zircon little crystals, microscopic crystals that can be separated from the rock, as you can see in that photograph there. Now, the age of these zircon crystals, based on uranium decaying to lead, was 1.5 billion years. 1.5 billion years. However, something interesting. As you go down the drill hole, you can see in this table, at deeper depths, the in-situ temperature rose. That's right. At nearly 4 kilometres down, the rock was at 277 degrees. That's more than twice the boiling point of water. That's how hot the rocks were at that depth. And in that last column, you see that helium percent, okay? That number represents the percentage of the 1.5 billion years worth of helium that was still in those zircon crystals. At only 750 metres, the 1.5 billion years worth of helium, 20% of it had been lost and 80% had been retained in these crystals. You might say, so what? Well, it's very significant, as this research discovered. Why? Because helium leaks out of these crystals. It's only a tiny atom. It's the second smallest atom. You've got hydrogen and then helium. And you've got this crystalline structure of the atoms in a pattern like you see in the diagram there. And the helium atoms can slip out their way between the zirconium and silicon and oxygen atoms. And the hotter the crystal makes sense. It makes sense that the faster the helium leaks out. Why? You heat the crystal, the atoms vibrate more dramatically, so the helium atoms get more energy and they slip out more easily. And of course that makes sense. In that last table, the deeper you went in the hole, the hotter the temperature, the less helium that was still left. Now, based on this, an experiment was proposed. We know that the hotter the zircons, the faster the leakage rate, as you can see in that graph. Now, don't get fazed by these diagrams and graphs. They're really simple to understand. And we can make a calculation. The helium lost divided by the time is what we call the leakage rate. And so we wanted to look at this data in this drill hole to see if you plugged in 6,000 years, what would the leakage rate be? You'd have lost a lot of it very quickly. It'd have to leak out very quickly in 6,000 years, whereas if these rocks were really 1.5 billion years old, to still have 80% of the helium in some of those zircon crystals meant that the leakage would have to be very slow. Okay? So we set up an experiment because, you see, no one had before measured how quickly helium leaks out. And so we published this prediction on this graph, which is temperature versus leakage rate. Diffusivity is just a fancy term for leakage. Okay? You can see that from that table I showed you before of the different depths and different temperatures, you can see the top one there is the 6,000 year line. That's how fast the leakage would have to be if all that helium leaked out in only 6,000 years. But if it leaked out in 1.5 billion years, it would be a lot slower, so that's further down in the graph. And the factor of difference is 100,000. Okay? Now, we published this prediction in the year 2000, and then we did the experiments. Now, we were laying our necks on the line because we could be proved wrong just like that. What happened when the results came in? Bingo. The data matched exactly, not even slightly off, exactly to the 6,000 year line. And so it was done in a world-class laboratory, actually at Caltech. And the experimental data verified the 6,000 year prediction and totally annihilated the 1.5 billion year prediction. Isn't that incredible? And when you take the individual samples with the amount of helium left and do a calculation of the age from the leakage rate, the average was around 6,000 years. And so that means, what does that mean? It means that these two clocks were ticking at different rates. The helium leakage clock, we know what leakage is all about. We can study it from well-known scientific laws, whereas people don't fully understand how radioactive decay occurs. That means the only way these two clocks could be reconciled is, in a sense, a real sense, that 1.5 billion years of the nuclear decay occurred during 6,000 years of helium diffusion. Since helium diffusion is a known measurable property that we can understand the physics of it, that means the radioactive decay clock had to have been speeded up by 100,000 times. And that, we believe, occurred during the flood.